Right, we're going to be talking about particle interactions and electron capture, primarily within the context of astrophysics. So what we're going to do is we're going to talk about the idea of a star, and we're going to talk about its life very briefly. So when a star is first formed, typically it's burning hydrogen and it stays on something called the main sequence for most of its life. Then when it comes to the end of it, it starts fusing hydrogen to helium, and when it starts fusing helium, it grows quite dramatically into a red giant. And there's not very much we can do in terms of displaying the size difference, but it's about 100 times larger than the original one. Inside this giant, we have a smaller star that's being formed out of the core of the fusion reactions that are actually occurring inside it. The outer atmosphere, that's this area here, is primarily a hydrogen and a bit of helium. The process continues producing things like carbon, nitrogen and oxygen, and depending on the size of a star it can even go all the way up to iron, which has the highest binding energy. Binding energy is something that's covered in year 2. We're talking about year 1 at the moment, but essentially binding energy is the amount of energy required to separate nucleons within the nucleus, and iron has the highest and therefore is the most stable of all of those elements, or of all of the elements that is there in terms of their nucleus. Now what happens is that the outer atmosphere of this star will be shed. It will literally disappear into some kind of nebula-like, and disappear out into interstellar space. And what we're left with is the innards of this star. And this star is called a white dwarf. Now the size of this star is quite small, so it's about the size of Earth. And it's essentially very, very compressed matter. So it's got something called electron degeneracy. The electrons are essentially pushed out into higher energy levels than they used to. So we can think about different energy levels in terms of how difficult it is for them to escape from the nucleus that's in there. And what's happening is they've been pushed out from the lowest level, the ground level, and they're being pushed into higher and higher levels, unnaturally high levels for those electrons. What actually happens then is, as gravity starts pulling it inwards, so there's quite a considerable pressure for these electrons to continue going to higher and higher levels, but the reality is that they can't go any higher. At a certain point there is kind of a maximum level which they can actually go, and the next level is actually to go and be a part and join oops, become a smaller star, and again, and this star going from here to here, this star is known as a neutron star. And the electrons are spinning around like wild in this situation. And the process by which it gets from being a white dwarf to a neutron star is quite interesting in terms of the physics. What happens is we have a proton that interacts with an electron through the weak force. It has to be weak force because the electron is a lepton. And the electron gets captured by the proton, forming a neutron. If we look at this in terms of quark composition, we have an up-up-down quark here, and an up-down-down quark. In the process of capturing the electron, an up quark changes into a down quark. Now, using the conservation rules, we still have to have the same lepton count afterward as before. If we look at the baryon count before, we have a proton, so that's 1. That's it. We have electron lepton count of 1. We have a charge of 0. This being, since the proton is positive, electron is negative. Strangeness we don't need to worry about because neither are strange particles, but it's essentially 0. After the interaction, we have to balance these. So we already have in the neutron, we already have a baryon count of 1. So whatever other particle is involved in this is not a baryon. Looking at the lepton count, we have no leptons there, so at the moment it's 0, so we have to add something to it, and we have to add something that has a +1 lepton count. Charge-wise, we are presently at 0, so the particle that's missing, neutrons being completely chargeless, so the particle that's missing is going to be chargeless. And again, there's no strangeness involved in this, so we don't need to worry about that. So what actually happens here is the only particle that actually satisfies these rules is going to be a neutrino, and specifically an electron neutrino. Now this is a weak force interaction. Now typically your papers don't really talk about the weak force in great detail in terms of which direction the particle is, but it's assumed that this is a W+. So what happens when this Feynman, when the interaction that this Feynman diagram actually shows us, is that we suddenly end up with a massive amount of neutrons, and this tends to these stars tend to spin quite rapidly as they actually collapse in on themselves, conserving angular momentum. And although neutrons are negative, have a neutral charge, the quarks themselves are charged. So we'll dip into year 2 a little bit, and just explain that when charged particles are moving, so when charge is actually moving, we end up with a strong magnetic field. Now, the letter we use for magnetic field is actually B. So there's a very hugely strong magnetic field that exists around neutron stars. As they form, going from here to here, there's a massive release in every direction of neutrinos. And neutrinos don't tend to interact very much at all with the universe around it. At least 99% of it will never interact with anything throughout the whole of the life cycle of the universe. Instead, these neutrinos continue to exist pretty much forever. They're very weakly interacting particles, and because they have a very small cross-sectional area, they will tend to interact with, well, pretty much nothing. However, what is quite interesting is that we can create detectors, and we do have detectors like the ice cube on the Antarctic and several other experimental devices around the world, where we can interact and look at these particles. So interestingly enough, CCl4, which is the chemical formula for dry cleaning fluid, is actually used in great amounts in actually looking at this in some of these detectors. We can actually see this. So if we see a massive burst of neutrinos from a certain point in space, we know that there's been this kind of collapse has occurred, and we know that inside that star we have this interaction occurring. If we were to write this down as an interaction, what we have is a proton plus an electron becomes a neutron plus an electron neutrino, which disappears off into the horizon and can be detected. So as we look around space, we can actually see these things occurring because of the amount of electron neutrinos that are being released by the star as it collapses in from a white dwarf to a neutron star. And this tends to happen very rapidly. The collapse from here to here only takes a few fractions of a second, and it will then, depending on the size and the amount of gravity, it will continue to collapse into this. The next step, if there's enough gravity, is to produce a black hole. And what happens inside a black hole is slightly more mysterious than what happens inside a neutron star, because black holes don't really release information about what's inside them. Anyway, that's hopefully useful to you if you're interested in astrophysics and combining it with something to do with particle physics.